There's something kind of neat about factoring polynomials when you correlate that information with the graph of the related polynomial function. What we know is that x minus a is a factor of a polynomial if and only if x equals a is a zero of the polynomial function. So what that means here, the if and only if, this is a biconditional statement that's actually been rewritten as one statement. What this tells you is if x minus a is a factor of a polynomial, then x equals a is a zero of that polynomial function. And conversely, if x equals a is a zero of the polynomial function, then x minus a is a factor of that polynomial. So what we're going to do is we'll look at example 6.2.4 to kind of confirm this. What I'm going to do here is we're going to look at that function y equals, or f of x equals, x minus 7 times x minus 5 times x minus 3. Now obviously this is in factored form. This is going to show us that this factor x minus a, all right, tells us where the zeros are, right? And we did this in the last chapter. If we set this equal to 0, when does this equal 0? That's when x equals 7, when x equals 5, and when x equals 3. That would make that expression equal to 0. Well, here what I've done with my grapher calculator, and I'll try to make this visible to you all, is I've put the function in there. It doesn't come out nice and pretty because it extends into the next line down, but I've written that function y equals x minus 7 times x minus 5 times x minus 3. And we can look at the graph of that function, and we can see where those x-intercepts are. The x-intercepts, again, are the zeros. We're not going to use the calc menu to calculate where the zeros are, although that's a neat little trick. What we're just going to do is look at our table, all right? So we're going to take a look at our table, and we can see in the table here that there is a 0 at x equals positive 3, at positive 5, and at positive 7. Okay, so we got a 0 there, a 0 here, and up, we got a 0 at 3. So this tells us where all of our zeros are, all right? This is just a quick way to confirm that those numbers, 7, 5, and 3, are actually zeros. Now notice the way that this looks. X minus a, so in this case x minus 7, so 7 is a 0. X minus a, in this case a is 5, and so 5 is a 0. X minus a, in this case a is 3, x minus 3, so 3 is a 0. Now what we can do is we can extend that out to sort of further our cause. If we are given zeros, then we can write a polynomial function that has zeros at those specific locations, all right? So this allows us to create functions. This allows us to manipulate situations that we're given. So if we're told to write a polynomial function that has zeros at these values of x, then what we would do is write either y equals or f of x equals, it doesn't matter, y equals x minus each of these numbers, all right? So x minus 2, and x minus 1, and x minus negative 3. I'm going to write that as x plus 3. All right? This is the polynomial function that has zeros at these 3 locations. 3 zeros means it's going to be a degree 1, 2, 3 polynomial. Usually it's not acceptable to just leave it in this form. What we would need to do is actually multiply this out and find the polynomial function in standard form that has those zeros. So this will sort of correlate to example 6.2.2 that we did in the previous video. And that's fine because we could always use more practice multiplying. And on the last example, I didn't really do too much with multiplying a trinomial by a binomial. So I'll multiply these first 2 factors, and this gives us x squared minus 2x's and 1x make a total of negative 3x's. Negative 2 and negative 1 make positive 2. And I'll multiply that times x plus 3. Now, multiplying a trinomial times a binomial, it's still the distributive property, all right? So nothing fancy is happening here. What I will do is I'll kind of write this out in maybe a longer way than you would need to write it on your paper, just so that you can follow along with which items are multiplied by which. So what we're going to do is we're going to take each of these items, 1, 2, and 3, each of those by these 2. So for the first one here, we're going to take x squared multiplied by x and 3. And then we're going to take negative 3x's times x and 3. And then we're going to take 2 times x and 3. All right, and so we're going to have to do a lot of multiplication, but this multiplication is all pretty easy. And you can probably skip writing this step in future exercises. Just make sure that you are being attentive to all of your signs and all of the things that you need to make sure that you multiply by each other. All right, so I've multiplied all those. The last step here, we just need to combine our like terms. All right, we just need to combine our like terms. This x squared, our quadratic term, is going to cancel out, and it's going to become they're going to add up to 0. We're left with x cubed minus 7x's plus 6. All right, now that form right there, x cubed minus 7x plus 6, if I asked you to write that in factored form, most of us would be stumped on that because it's not an x squared, it's an x cubed, all right? And that can be a little bit confusing for us to manage. But given it in factored form, we can write it in standard form. So that's kind of an interesting situation. Now, if I were to graph that function, here's where I want to stretch us a little bit. I am going to graph this, x cubed minus 7x plus 6. And I do care about what the graph looks like a little bit, but what I'm mostly concerned with is the table. All right, and so I want to do that. I'm going to take a look at the picture here. When I type in that function, I get the graph that looks like this. I can't see the maximum here, the little local maximum up at the top there. It kind of goes out of the screen and comes back down. But we can see where our zeros are, and our table confirms that. Our table said that at -3 there's a 0, at +1 there's a 0, at +2 there's a 0. And so all of our zeros are accounted for. All right, kind of a neat trick.